In this video, we'll start investigating how we can train neural networks, and for that we'll look at the main principle behind training neural networks, which is known as empirical risk minimization. Now, we've seen the mathematical derivation or mathematical expression for what we mean by a multi-layer neural network, and in this description there are these parameters which are, for instance, the connections between the hidden units on the input layer, the first hidden layer, the connections between the first hidden layer and second hidden layer, then the connections between the last hidden layer and the output layer, as well as the bias vectors for each of the layers, the hidden layers and the output layer of the neural network. And so far we haven't talked about how we can actually find good values for these parameters such that our neural network will have the correct behavior, will solve our problem that we're trying to solve. So what we'll see in this video and the following videos is how we can train a neural network to develop the right behavior to solve a given problem. One of the problems we'll often talk about and we'll focus on is a problem classification. And a good problem to keep in mind when we're discussing training neural network is one where we would have an image where there is a particular character, say a 3 in this example, and we'll assume that we have some data where someone has told us that, for instance, for this image, this actually corresponds to the character 3. So we'll assume that we have some data where we have an input x and the associated target y that we must predict based on the input x. And for a character prediction, then x would be the row-wise vectorization of all the pixels in the image. That would be an example of an input to use, an input representation for an image. Okay, so that's a good problem to keep in mind while we're talking about training neural networks. So the specific algorithm that we'll be looking at for training neural network is going to be based on a very general principle in machine learning known as empirical risk minimization. So in a nutshell, the idea is that we'll convert the problem of training a neural network into an optimization problem. So I'm going to call theta the set of all my parameters in a given model. In the case we're interested in, theta is going to be all the parameters in the connection matrices, the W matrices, as well as the bias vectors B for all the different layers. I also note xt as the TF training example in some set of training images that we'll use to train our neural network. So xt here is a vector, and it's the TF input vector in my training set, and then yt is the associated, so the TF label or target that I have to predict based on x. So again, xt could be the image of a character, and yt could be the category associated with that character. So in empirical risk minimization, we'll frame the problem of learning or training a model as the problem of finding the parameters which minimize this objective here. This objective has two parts. The first part is the average of a loss function L that compares the output of my neural network with the expected or the correct answer yt. Okay, L is going to be what is known as a loss function, and it compares the output with the label. And also I'm going to add a term, omega of theta, which is known as a regularizer. And what it does is that it penalizes certain values of theta, certain values of my parameter, which for some reason we think are not good values, that will not work well on when we try to solve problems on new images, say on new examples. And then we have a parameter here, lambda, which is going to be a hyperparameter, which is going to control the balance between optimizing the average loss and optimizing the regularizer function. So here, because we have this argmin, really we're converting our problem into an optimization problem. We're trying to minimize a particular objective. Ideally, we'd like to optimize classification error if we're doing classification. So we'd like to optimize the actual percentage of errors that our model is makes on the training set. However, this function is not a smooth function. If we wanted to optimize the number of times that the output class by our model, which is the class which is associated with the biggest probability based on the output probability given by our neural network. So the number of times that the most likely class according to our model is wrong, this is actually a function which is not smooth. So it essentially looks something like this, where this is when we have an error of 0 when we have where the correct class has the highest probability, and then we have an error of 1 when the correct class doesn't have the highest probability. So this function, which looks like this, is not smooth, so it's a very hard function to optimize. So instead, what we do is we usually use a loss function, which is going to be a surrogate of what we truly want to optimize. So for instance, we might try to actually upper bound the real thing that we want to optimize with something smooth. So if we could somehow take this function, say our loss function look like this, and have a smooth version which maybe look like this, then we might try to optimize this as well and hope that because this is fairly close to that, then we are sort of optimizing the real thing. So this is the general principle for empirical risk minimization that we'll try to follow when training neural networks. And because we've casted our problem as an optimization problem, what's great is that we can leverage optimization algorithms from the optimization literature. And one algorithm that we'll focus on is the stochastic gradient descent algorithm. And this is an algorithm you've probably seen if you've taken a machine learning class, so I'll just briefly describe it here. So what the algorithm does is that first it initializes the parameters of our neural network, so all the connections and biases in our neural network in some way. Often it's initialized randomly. And then for a certain number of iterations, which we have to specify n here, what we'll do is that we'll iterate over our training set, and for each training example, each pair xt, yt, we'll figure out a direction that we'll explore that we'll consider for updating our parameters. And then a natural direction to use for a given training example is the opposite direction of the gradient of the loss n plus the gradient of the regularizer. So we go in the opposite direction, so we have a minus here. So remember that the gradient is telling us in what directions I get the biggest increase if I change a certain number of variables. So if I take my loss plus my regularizer, if I take the gradient of that, then this will give me in which direction, and I take the gradient with respect to my parameter, this gives me the direction in which if I follow this direction in changing my parameter, I'm going to get the biggest increase in the loss plus the weighted regularizer. So if I go in the opposite direction, I should get locally the biggest decrease in the loss plus my weighted regularizer. So I use that as my direction. So that's going to be my direction delta. And then I'll just take my parameter and I'll update it by adding a step size or learning rate alpha, which is another parameter I have to specify, a hyperparameter, times this direction delta for updating my parameter. So I'm taking one step in the direction that is locally most likely to decrease, that's going to decrease the most my sum of loss plus regularizer for my training example. And so I repeat this operation here for each training example in my training set. And then I repeat this whole loop n times, which is the number of iterations, or sometimes we'll call that a number of training epoch over all my training examples. Okay, so if we want to apply this general algorithm of stochastic gradient descent, I need the following items in this recipe. I need to define my loss function, this function L. I need a procedure for computing the gradients. Ideally, I want a procedure that's efficient because I'm gonna do a lot of updates. I'm gonna compute this term here often. I need to choose a particular form for my regularizer, and given that form, I also need to compute the gradient with respect to of that regularizer with respect to my parameter theta. And then I also need to specify a way of initializing my parameters. So what we'll do in the next videos is we'll go over all of these different items in this recipe so that we have all the items we need, all the ingredients to apply stochastic gradient descent and train a neural network.